So, let us carry on with the discussion on the temperature jump technique. So, this is the last equation we kind of derived yesterday. So, this is the one I am talking about, equation number 18. So, where the change of the concentration of the fluid state with temperature is given by this with a negative sign delta H naught over R T square times m, and then the most important thing is that this change of the fluid state, whether the concentration of the fluid state is going to change or not, will depend upon two things. One is the delta H naught and the other one is the m, right. Okay. So, this is what m was, this is how we defined m. So, it is 1 by concentration of u plus 1 by concentration of f, and then we went for a finite change. We went for a finite change and this is what we got, right. This is one of the most important equations we have for laser or for a temperature jump relaxation method. So, again as we see out here, the change in the fluid state depends upon two things, delta H naught and m. So, if delta H naught is 0, then there would be no change in the concentration of the fluid state, which means is that if you are going to have a temperature jump, you better have a change in enthalpy, right, otherwise you are not going to see any change. And good for us that most of the processes we are studying are accompanied by enthalpy changes, and hence that is taken care of. Okay. Now, the other important aspect was this was the last thing we were discussing. What about m? What is the dependence on m like? So, when can m be 0? M can be 0 if it is 1 by infinity, that is the denominator is 0, rather denominator is infinity. So, the denominator is comprised of two terms, the reciprocal of the concentration of the unfolded state and the reciprocal of the concentration of the folded state, right. So, what it means is that for these one of these, even if one of these go to infinity, that means if concentration u is equal to 0 or concentration of f is equal to 0, then the denominator goes to infinity straight up, right. So, then what it says is that if concentration of u is equal to 0, that means if concentration of u tends to 0, this is we are talking about this one, then we are where we are completely at the fluid side, and when concentration of f is 0, then we are completely at the unfolded side, and hence if you are at the two extremes, you better not use your temperature jump method, because you are not going to get much out of it. Why? Because m essentially will go to 0 for you, right. Okay. So, how does this translate into a measurement? The way it translates into a measurement is like this. Say for example, consider a thermal denaturation profile, right. So, let us look at a thermal denaturation profile of a protein, and suppose you are looking at a certain change in a spectroscopic signal, say its fluorescence, it is y, okay, and this is how it looks like, right. So, I can say this one is your folded state and this one is your unfolded. Okay. Now, on the x axis what we have is we have temperature, that means we are doing a temperature induced denaturation, that is thermal denaturation. Okay. So, now let us now think about this. We pick out few temperatures, we pick out, say this is T1, T2, T3, T4, T5, T6. Now, let us go interval by interval. Okay. Suppose I am making a temperature jump from T1 to T2, right. Suppose I am making a temperature jump from T1 to T2 to T2. Now, throughout what your temperature jump is doing, it is observing, or what it is trying to give you an idea of the change in your concentration of the fluid state, Okay. Now, if you are jumping from T1 to T2, would this be a logical way of doing it based on the discussion we had before? Why not? Completely folded. So, you look at this, where is T1 to T2? Even if you go from T1 to T2, you are still on a folded baseline, is not it? There has been no unfolding. So, that means even if there is any change in delta f, what would that be? Very, very small or almost close to 0. What does it mean? It goes back to m. So, because it is completely folded, then what happens to the concentration of u? It is very small, being close to 0, hence the denominator goes to what? Infinity, right. So, if you are on the folded baseline, you would not be able to do that, because you would not be able to do a temperature jump, because even if you do a temperature jump, the change in the concentration of the folded state would be very small, too small for you to detect anything, even spectroscopically. Is that clear? Because you see on your y axis you have the spectroscopic signal y, right. So, this folded baseline from T1 to T2, because it is kind of parallel to the x axis, what does it mean? That means your y is not changing, that means there is almost no change in spectroscopic signal, you are not going to be able to figure out anything, right, and you are not supposed to, because you are still in the folded baseline, you are in the folded state. Clear? Now, let us go to T1 to T3, it is a little better. It is a little bit better, because when you go to T3, you have just started unfolding the protein, is not it? Okay. So, obviously, T1, the gap between, so if I write this one is not logical, say T1 to T2 is not logical, then I can write say T2 to T3, T2 to T3, this would be better than T1 to T2, at least little better, because we have a small change in the concentration of the folded state. But still keep in mind, look at the change in the spectroscopic signal from T1 to T3, or rather T2 to T3, it is not that high, is not it? It is still small. Okay. Now, suppose you make a change from T3 to T4, is that a good one of doing it? Look at T3 to T4. So, this is T3 to T4, right, this is T3 to T4. Here you have a huge change in the concentration of the folded state, right. You have moved from a place where you have just started unfolding to a place where there is a huge amount of unfolded state present, that means the concentration of the folded state has decreased. So, then T3 to T4 would be a very good interval for you to do a temperature jump, right. So, then T3 to T4, won't you try to do it, because you have a huge change in the concentration of the folded state or unfolded state, and your spectroscopic signal is also changing by this amount, your spectroscopic signal is also changing. Okay. What about T4 to T5? There is still a change. Okay. Now, see, T4 to T5 is also logical. So, T4 to T5 is almost like T3 to T4, right. Okay. Now, tell me this, the interval between T3 to T5, right, the interval between T3 to T5, what does that signify? You know, what is the significance of that interval? That is your transition region, right. And if you go back to your thermodynamics, remember when we talked about delta G calculation, we said that we cannot do any delta G calculation based on your completely folded or completely unfolded state. We would be better off doing a delta G calculation where we have, right, in the transition region where you have appreciable amounts of both present. The same thing is applying here. You can only have a decent change in spectroscopic signal if you are in the transition region only, because in this case the transition is sharp and you have a detectable change in the signals, even you have a small temperature jump, does not matter what your temperature jump is. Clear? Okay. So, obviously then you can understand from T3 to T5, this would be the region where you would try to focus on your experiment, because beneath T3 you would not be getting much, and above T5 what would happen? Again you would not be getting much. Why? Because now you are in the unfolded region where your concentration of folded state is really low. Clear? So, that is why when people typically do experiments, remember when people typically do experiments, this is the region they want to target. based on this logic that we just discussed. Now, please keep in mind, every protein depending upon what type of protein you are taking would not be giving this amount of or this cooperative a transition. Different proteins would be having different transitions. For example, let me just give you a quick plot. Say for a protein, this is a spectroscopic signal and this is temperature, right, and its transition looks something like this. Say its transition is looking something like this, right. So, this is your unfolded baseline. So, at least on the unfolded baseline you can see it is kind of tapering off, not much of a change, but do you have a folded baseline? You actually do not have a folded baseline, right. Now, tell me this, if I have here T1, here T2, here T3, throughout these temperature intervals would you not be having changes? You would be having changes, right. So, if you would be having changes, then you can easily monitor or you can easily go for your temperature jump technique within this interval, because that is your transition region. Okay. So, then this is T4, T4 and so on. Is it clear? So, again you take any protein, but before you do a temperature jump, what would you rather do? Tell me, before you would do a kinetic measurement, assuming the fact that you have a temperature jump instrument with you, right. I have not talked about the instrumentation, I will just go over it briefly in a couple of slides. But again, the question is, if you have a temperature jump instrument with you, right, you can do a temperature jump, you are given a protein which you not know much about, would you go for a temperature jump straight away? Would you start with a temperature jump? Yes or no? No. What would you rather do first? Yes, you would do a thermal denaturation. That means that is why equilibrium is so important. You first do a thermal denaturation, right, just based on CD or fluorescence or whatever, to see where the transition is, because blindly if you start from any particular temperature you might not be getting any signal, which will tell you that maybe there is not much happening out there. Maybe either you are on the very folded baseline or you are on the very much unfolded baseline. Okay. So, that is why you first take a protein, and before you do any experiment like this, the first thing you do is you go for a equilibrium denaturation experiment. If you are doing a temperature dependence, then you do go a thermal denaturation. If you are doing a rapid mixing, then you go for a chemical denaturation, but you have to have that thing in hand. Okay. So, that is typically what your temperature jump is all about, right, and again you cannot just take any arbitrary temperature, you have to make sure that you are in a region where there are appreciable amounts of both present. That is the bottom line. Okay. Only then would m be significant, remember, otherwise m would be close to 0 and hence your change would also be very small, right. So, this was about the theory of the temperature jump. Now, going back to the slides, I was talking about relaxation technique. This was the temperature jump technique we had talked about yesterday. Are you guys clear about the concept behind how the temperature jump is done, how you have to go from one equilibrium to another equilibrium and so on, what relaxation looking at? So, this we had completed, this we had seen yesterday, okay, and this is where I stopped looking at the slides. So, the principle is to make a rapid change in temperature delta T, assuming delta H is not equal to 0 and m is not equal to 0. That is what we just discussed. As a result of this rapid change, the folded protein finds itself in a non-equilibrium situation. It is a repetition of what we did yesterday. Since temperature increase has shifted the equilibrium constant, good. Thus, the folded protein adjusts itself to the new equilibrium situation at the higher temperature T2. That is why we always write concentration of F equilibrium comma 2. 2 means at temperature T2, right. And the time it takes, that is the folded protein takes to adjust to this new equilibrium situation, is known as your relaxation time. That is why it is called a relaxation method, because you are changing something and then because of that change the protein is relaxing to the new change. That is why it is called a relaxation method. Okay. So, this is about instrumentation. How do you actually do it? right. There are two ways of doing it, two popular ways. One is using a capacitor discharge. So, you suddenly discharge a capacitor, right, you have a temperature increase and then you do it. The other way of doing it is using a laser, right. Now, this is how you do it. So, look at the block diagram, it is just a schematic and try to understand it. So, in the sample cell you have your sample, right. So, this is the sample cell, you have your sample, say your protein in buffer, right, it is at a certain temperature, right. Now, you are trying to increase the temperature from T1 to T2, making sure that T1 to T2 are kind of in the transition region, at least the spectroscopic change between T1 to T2 is decent enough for you to get something out. Now, what does this pump laser do? So, look at this pump laser. What does this pump laser do? I'll show a better diagram in the next slide, but let me tell you this. Okay, you have to do a temperature jump. That means you have to increase the temperature. The pump laser is such that you have your protein in buffer. The sample, I am not telling you which part, but the sample absorbs the laser. The sample absorbs the laser radiation of the pump laser. Now, because the laser is appearing, the laser light is appearing in pulses, that means like this, it is not a continuous light, it is appearing in pulses like this. You have a laser light, again you have a laser light, again you have a laser light, right, it is called a laser pulse, and this pulse is very small. You have a huge amount of energy being thrown into the sample. Now, do not worry about the actual details of it, right. So, now the sample absorbs it. The moment the sample absorbs your laser, what will happen is, because the laser is putting in a lot of energy, the sample will undergo an increase in energy. So, how would the sample respond? It will undergo an increase in temperature. The moment you undergo an increase in temperature, the protein now will also respond, right, and then you look at the change using a detector, okay, using a detector. But what is the probe laser doing? This is what the probe laser is doing. You are pumping at a different wavelength. It is called a pump laser because you are pumping energy into the system. That is why it is called a pump laser. Your system is absorbing the pump laser and undergoing an increase in temperature. But now you are probing. Probing means you are probing the change. You are probing the change in the concentration of the folded state of the protein, but how is that coming out in terms of a certain spectroscopic signal, right? And that signal you are probing with a different laser called a probe laser. So, this means this is the one you are using to monitor the change in the concentration of the folded state. Just hold on, I will tell you in a little more clear terms what is the difference between the pump and the probe laser. What am I referring to? It is actually very interesting. Okay. So, do you understand now the difference between a pump and a probe laser? So, pump laser, what it does is it helps you increase the temperature, that is it. It does not help you detect. The probe laser comes in because you are now probing, right, you are probing. So, the pump is pumping in energy, increasing the temperature. The probe laser, as the name suggests, is it is helping you probe the change in spectroscopic signal, that is why it is called a probe laser. So, you are probing, you are searching, you are probing for the change in spectroscopic signal. Okay. Now, this is a very simplistic diagram, this is how it happens, but how does it actually take place? Okay, this is an actual setup. Okay, this is an actual setup, not that you have to know it by heart, but let us try to understand what happens. First of all, let me go back to the sheet and tell you exactly what is trying to take place. So, you have a sample cell. So, this is your sample cell, okay. This is your sample cell. In this, what you have is your protein in buffer, but I am taking D2O buffer, I am not taking H2O buffer. I will tell you a reason for that, right. I am taking a D2O buffer. That means instead of H2 I am taking what? Heavy water, right, you know D2 is available. Okay. Now, my laser is coming in, if you remember my laser is coming in. So, based on that block diagram, the pump laser comes in like this and goes into this. So, this is my pump laser. Now, listen to this very carefully. what do you think, which component in this sample cell do you think is absorbing the pump laser? D2O, excellent. See, the concentration of the protein is typically, depending upon the size of the protein, is typically in the order of higher micromolars to some millimolar, right. But what is the concentration of D2O? It is much higher, is not it? You look at the concentration of water. What is the concentration of water? Neat water. Neat water is 55 molar, if you would remember. So, then accordingly with the density you can easily get the concentration of D2O, it would also be similar. Okay. So, the concentration of D2O is much higher. So, the more D2O you have, the more you will be able to absorb the energy, okay, because you have more D2O molecules, as simple as that. Now, the pump laser has a wavelength of 1.9 micron, that means 1900 nanometers, that means 1900 nanometers. Okay. Why am I using 1.9 micron? I am using 1.9 micron because if you would ever look at the IR spectrum of D2O, I am only going to show you that the IR spectrum of D2O has a small absorption band at 1.9 micron, and it has a much bigger absorption band elsewhere. But there are reasons why you always go for the small absorption band, okay, to maintain uniformity in heating, but that is separate, do not worry about it. Again, so at 1.9 micron your pump laser is coming in, because your D2O has an absorbance out there, it would absorb the 1.9 micron. Is it clear? Okay. Now, the moment it absorbs the 1.9 micron, I will tell you what happens is the pump laser, each pulse is on for about say 10 nanoseconds. Each pulse is on for about 10 nanoseconds and with pretty high energy. So, the D2O absorbs this pump laser, that means this wavelength. Because it absorbs, what happens is it has got thermally excited, because it has absorbed the laser energy, right. The moment it is thermally excited, it is at a excited state, right. Now, what happens is it will relax, because it cannot stay at the excited state forever, it will relax. Now, on relaxation what would it do? It would get rid of the excess energy. Now, tell me who is going to pick that excess energy up? The protein would. The protein would be picking the excess energy up. So, you can realize one thing, you are not directly heating the protein. What are you directly heating? You are actually directly heating the solvent, which is D2O. D2O is getting excited to an excited state, then it relaxes, it gets rid of the excess energy, and that energy is taken up by the protein, and the protein also undergoes a rise in temperature. That is how you bring about a change in temperature in the protein molecules. Okay. Now, this can happen very fast. Much faster than what we have encountered in the rapid mixing techniques, even with a microfluidic mixture. This can happen in the order of this D2O can let its energy go to the protein in the order of say 100 picoseconds or so. That means, the faster a protein takes it up, depending upon the size of the protein and all these things, the faster essentially would be able to monitor the change. Okay, but there is a limitation, I will tell you what the limitation is, right. So, this was about the pumping. That means, now you have done what you have done is you have increased the temperature, the protein has undergone a temperature change, and the protein is now at a higher temperature T2 from T1 because of absorption of this laser pump or laser wavelength. Now, how would you probe? Now, what is known is when we will talk about IR, what is known is that proteins typically have well developed absorption bands. This is called a amide 1 band. Amide 1 band, depending upon the structure, in the region of 1640 centimeter inverse, say 1635, 1640 centimeter inverse, right. So, Well, you can write 1640, 1630, either way is fine. Now, remember there was another laser. What was that laser? That laser was the probe laser. Okay. So, the probe laser was coming from this side. The probe laser was coming from this side. Now, what happens is, there is a reason why I have written 1630 and 1640. So, this is what happens typically, right. If you take an alpha helical protein, if you would take an alpha helical protein, okay, I am just going beyond what I should right now, but let me give you the significance. If you take an alpha helical protein, what happens is, at the folded state, the alpha helical protein typically has an IR absorption at 1630 centimeter inverse. Okay. Now, when you unfold the protein, so this is folded protein. When you unfold the protein, the same absorption band that is amide 1 band shifts to about 1645 to 1650 centimeter inverse. Okay. So, this is your unfolded protein. Now, this is what the probe laser does for you. The probe laser has a wavelength or a frequency corresponding to 1630 centimeter inverse. Now, tell me, the concept is very simple. Your probe laser is always probing what? At the peak of your folded state, which is 1630. That is the absorption peak of your folded state. This is IR, right. Now, what is going to happen if I am going to decrease the amount of folded state and increase the amount of unfolded state? What is going to happen to the intensity of this IR band? It is going to decrease. So, that means the probe laser is actually probing the change in intensity of this band at 1630 centimeter inverse as a function of time. Did you get my point? So, the probe laser has a fixed lasing frequency at what? 1630 centimeter inverse, just 1. So, if the probe laser is parked, is fixed at 1630 and you are doing a temperature jump, because the protein is unfolding, that means the intensity which was there at T1 at 1630, when you go to T2 it would decrease. Because it would decrease, the probe would pick it up, because it is always fixed at 1630. So, it sees that as you have increased the temperature and the protein is responding, the probe, what does the probe see? At every time point it slowly sees that, okay, my intensity at 1630 is slowly decreasing as a function of time, and then you pick the kinetics up with the detector. That is what your probe laser is doing. That is why you have two different lasers. Okay. Is it clear how the experiment is done? This is how the experiment is done. Okay. Now, what about using D2O? This is why we use D2O. The reason we use D2O is that if you would use H2O, not D2O, if you would H2O, our life would have been much simpler if you would have used H2O. But the problem is, remember, where are you probing the protein at 1630? H2O has a huge absorption band at that place. Then whatever change you have in the protein would be masked by that absorption of H2O, because it has huge absorption. But the moment you do an isotopic substitution, what you do is, remember, your vibrational frequency depends upon what? 1 by 2 pi root over k by mu, and keeping force constant the same, because mu is changing, there will be shift in a vibrational frequency. So, you move a masking band out of the way and just look at the protein itself. That is the function of D2O. That is why you do it in D2O. Clear? So, there are few aspects you have to keep in mind. One is, you have two lasers, one is a pump laser, one is a probe laser. Second is, you are not directly heating the protein, instead what are you heating? You are heating D2O. D2O has a small absorption band at about 1.9 micron, that is the wavelength of your pump laser. The probe laser, say, has a fixed absorption wavelength of 1630 centimeter inverse. What is it probing? It is probing the change in intensity of the alpha helical band of the folded state at 1630 centimeter inverse based on your temperature jump. Now, typically the magnitude of temperature jump you do is between, like, it can be anywhere, I mean to get a decent change it can be say from 8 to 15 degrees Celsius or even more than that. So, your delta T, that is the temperature jump, is about 8 to 15 degrees Celsius or more than that. Okay. So, let me write that down. So, your delta T that is your T jump is typically between 10 to 20 degrees Celsius, it is typically like that. Okay. And if you are getting a change, then using all these things together you are getting the change. Okay. Now, just to tell you the significance of one more thing, remember I told you that the pump laser has a pulse of 10 nanoseconds. That means, when the pump laser is coming in, it is coming in with a pulse of light which is looking like this, and the width of this is 10 nanoseconds. It is called something referred to as full width at half maximum, but do not worry about it. It is the width of your pulse, laser pulse. So, you can understand one thing, if the laser pulse is on for 10 nanoseconds, that means for 10 nanoseconds it is on and then it goes off and then it comes on again, it comes in pulses. So, within 10 nanoseconds you are actually not being able to detect any changes, because the laser pulse is always on during those 10 nanoseconds. You can only detect the change when? You can only detect the change when your laser pulse is off and your stuff is relaxing because of the new temperature jump. So, that is why typically here in temperature jump technique your fastest time scale is in the order of, the one I am talking about right now is in the order of say 30 to 40 nanoseconds or more. That means, anything greater than 40 to 50 nanoseconds you can easily probe using a temperature jump technique. But there is also a limitation on the higher side. If I start going into it, that will be too much of details, but what I am trying to tell you is that you started from a stopped flow which was the dead time was 1 millisecond, you went to a continuous flow where the dead time was 45 microsecond, you made a further improvement by making a microfluidic which the dead time was 5 microsecond. Now, using a temperature jump technique you are coming to a dead time which is about 50 nanoseconds. So, in this case I can write the dead time is about 50 nanoseconds, but people have been able to go much faster than that, but this is in general what happens. Okay. Right. Now, let us come back to the slide and tell you something about the instrumentation. Okay, just follow me, not that you have to remember it by heart, but just follow me. Okay. So, this is a laser, this is your starting laser. This laser has a wavelength of, you can see it is 1.064 micron, that is 1064 nanometers. Okay. It goes through something known as a Raman shifter. A Raman shifter, if you go through a Raman, for Raman spectroscopy there are two kinds of lines. What are the two kinds of lines you get apart from the Rayleigh one? Stokes and anti-Stokes, right. Okay. Now, remember, where does D2 absorb? I said 1.9 micron. So, that means I have to go from a wavelength of 1.1 micron essentially, which is 1.064, to a wavelength of what? 1.9 micron. So, I would do a Raman shifting and take the Stokes line, which Stokes line is that? That Stokes line which shifts or decreases its wavelength, or rather increases wavelength, that is decreases its frequency, increases wavelength from 1.1 micron to 1.9 micron. That is the essence of having a Raman shifter there. Okay. To shift your wavelength to that place, that is that value 1.9 micron where D2O can absorb. Okay. That is the use of the Raman shifter, right. Okay. Good. Now, you can see you are going like this. So, this is a mirror. So, this is M1, this is M2. What are the mirrors? The mirrors are just like guiding. So, they are just guiding the propagation of the laser beam after coming out of the Raman shifter. So, that means now you can see this is very important. What is the wavelength? 2 micron, like 1.9 micron. What is the pulse duration? You see this pulse, what is the pulse duration? Is 10 nanosecond, and this is the energy 20 millijoules per pulse. This is a decent enough energy. Again, do not worry about the actual value of the energy, but let me take it from me, this is a decent enough energy to bring about a increase in temperature jump, a detectable increase in temperature jump. Okay. Now, here is another mirror, say M3. So, this is your sample. You can see now this green line is your 2 micron, right. This now goes in, and what happens? Look at this point. This is the sample. This is the sample. In this you have protein and D2O buffer. Okay. But the laser is not illuminating your whole portion. It is the laser is a fine focus beam. It is going through only one point. Okay. So, that means at that point you are having a temperature change, isn't it? Because the other points where you do not have laser illumination, you are not doing anything. Okay. Good. So, this is your sample, and this is kind of a block which blocks your laser beam, because laser beams can be very harmful at high energy. So, you would take every precaution if ever you are working with a laser to be able to block it, so that there are no extraneous lights coming out. Okay. Good. Now, that is your what should I say, that is your pump laser, right. This was your pump laser. Now, we still have what, the probe laser. Okay. So, this is what your probe laser is. So, this is your probe laser. See, what is the frequency of the probe laser? The frequency of the probe laser can be tuned between 1600 to 1700 centimeter inverse. And let me tell you this, if you are going for alpha helix, what frequency would we go for? As you just said, 1630. So, again take it from me, you can tune the laser diode frequency, laser diode in such a way, the current and all these things, that it gives out typically that frequency which corresponds to 1630 centimeter inverse. Okay, you can do that. Okay. Now, once you do that, again you have a set of lenses. So, this is L1, this is L2, a set of lenses. Now, guys, tell me, where should this probe laser focus? Should it not focus at the same point through which the pump laser passed? Do you understand that? See, the pump laser is not illuminating your whole sample, it is only illuminating a certain area, certain point. So, if you have to get a signal change, where would you probe? You would not probe any arbitrary area of the sample. Where would you rather probe? You would rather probe at that place where your pump laser is passing through, because that is where you are having the change. So, the probe, that is why you can see you have this arrangement, and finally, where is the probe focused? The probe is focused at the same point where the pump is. So, this is called overlapping between your pump and probe beams, that you overlap these two beams, so that you get a detectable signal. And after that, this is your detector, and you have an oscilloscope and all these things. So, that is secondary right now, and you get your change. Now, also let me tell you this is a very good instrument if you know how to maintain it, if you know how to work with it. It is not that very many people have it in the world. It is actually a select instrument. I mean, if you compare with the number of groups doing research, the number of groups actually having this instrument is very small, merely a handful or more than that. Okay. So, in that sense, it is a rare instrument to be in possession of, let me tell you that. Okay. And if people are looking at protein folding unfolding, this is one of the better instruments that people can actually think of having, if they are really looking at all these kinetic changes and all these things. Okay. So, guys, this essentially is your laser induced temperature jump, because you are inducing the temperature jump, and you are even probing the change using lasers. One is a pump laser and the other one is a probe laser. Okay. I do not want you to remember all these things, I do not want you to remember this one, but at least, guys, remember the block diagram, remember the essence of what a pump beam does, what a probe beam does, and the principle of this technique. What I told you is, it is one of the ways it is actually being done in practice. Okay. Good. So, this then we are done with relaxation method. Okay. And the last technique that I am going to discuss with you, an experimental technique, is known as optical triggering of flash photolysis. Okay. So, optical triggering means you trigger using some sort of light, some sort of optical thing. What is a flash photolysis? Flash means it happens in a flash, it is like a camera flash. You see a flash, it happens in a flash. What is photolysis? What is photo stand for? Photons, right? What is lysis? Breakage. That means in a flash using photons you are breaking a bond, and that is how, or this would help you to monitor a certain change in folding or unfolding. Okay. How do we do that? So, for this again we go back to our dear old friend cytochrome C, right. This is the principle of the method. The principle is cytochrome C in the folded state, right, does not absorb or does not ligate or does not bind carbon monoxide. Instead, if you have to have cytochrome C bind carbon monoxide, where would you have to go? You have to go to an unfolded state, right. Now, suppose what you have done is you have unfolded cytochrome C with guanidinium hydrochloride, and you are passing carbon monoxide and guanidinium hydrochloride, and cytochrome C binds guanidinium hydrochloride. Okay. Now, this is what the method says. In the absence of carbon monoxide, that means you have not bound any carbon monoxide, the unfolding transition of cytochrome C begins at 4.5 molar guanidinium hydrochloride and gets completed by 6 molar. So, the Cm, which is, remember what the Cm is, right, it is 5.1 molar. Okay. Now, if this point was about the absence of carbon monoxide, the next point would always be about what? The presence. So, in the presence of carbon monoxide, the equilibrium is shifted towards the unfolded state due to preferential binding of CO to the unfolded state. That is what I just said. CO does not bind to the folded state, it preferentially binds to the unfolded state. That means, the moment you bind CO, what you do is you shift the equilibrium towards the unfolded state. Now, here unfolding occurs at a much lower denaturing concentration, with Cm being 3.7 molar. So, you can see what has happened. What has happened is, in absence of CO, the Cm was 5.1, in the presence of CO, the Cm has come down to what? 3.7. So, there is a difference by 1.4. Now, that is pretty high. Okay. Now, how do you see that in your experiment? See, this is what you are doing. This is a fluorescence intensity. Remember that fluorescence intensity, the trip intensity we are looking at, and on the x axis what do you have? You have guanidinium hydrochloride concentration. There are two curves you are looking at. There are two curves you are looking at. First, look at this curve. This curve. This curve is the one where guanidinium hydrochloride is bound to CO. Okay. Now, as was showed in the previous slide, see its unfolding transition is at about 3.7. So, this 3.7 would be somewhere here. This is 3.7 molar. Okay. This is the Cm, right, and then it unfolds. Now, this one is the one without CO. That means the cytochrome C, no CO. Obviously, it is more stable, right, and the Cm is much higher. So, this is, if this is the Cm, say this would be what? What was it? 5.1, I guess. 5.1. Okay. Now, look at the dotted line. What does it say? The dotted line at this dotted line, you have a concentration of 4.5 molar guanidinium hydrochloride. Okay. Now, just forget everything else, focus on the dotted line and the two curves. For the upper curve, which is the with CO curve, 4.5 molar lies in which part of the curve? Does it lie in the folded part or the unfolded part? It lies in the unfolded part, right. That means, your transition is already over. Good. Okay. Now, if you draw a vertical line now, that means you have not changed the guanidinium hydrochloride concentration, right. If you come to the other curve where there is no CO, where does this 4.5 molar now lie? It lies in the folded baseline. Okay. Now, do you understand the difference now? So, what you can do now is, now this is what the flash trigger is going to do, or the optical trigger is going to do. You take guanidinium hydrochloride with CO, rather you take cytochrome C with CO at 4.5 molar guanidinium hydrochloride. So, under those conditions, based on the forced curve, it is already unfolded. Clear? Now, what you do is, you know that if I remove CO, the protein from the unfolded state would immediately come to the what? the folded state. So, what you do is you shine it with a laser, right. That laser is absorbed by cytochrome C, and that laser helps in breaking the bond between the CO and cytochrome C. And remember, where the CO bind, where does the CO bind, you think? To iron. It is very simple. So, the bond breaks. The moment the bond breaks, what happens? No CO. How would the protein respond now? The protein will respond by going to the folded state, and then you monitor that relaxation. So, that is what an optical triggering is all about. Is it clear to you guys? I would not go more than this, but what he says is you take a bound, a CO bound cytochrome C in a high concentration of guanine hydrochloride 4.5 molar. For the CO bound cytochrome C, you are in the unfolded regime. You do a fission of your bond, you do a scission of your bond with light. The moment the CO is cleaved, the bond between CO and Fe is cleaved, what happens? The protein now realizes that I have to fold, because I am more stable at 4.5 molar without CO, I have to go to the folded state. So, it starts going to the folded state, and then you somehow monitor that relaxation using this technique, and that relaxation was triggered by what? Was triggered by that photolysis, and hence it is called optical trigger based on a flash photolysis method. Is the principle clear? Right, based on this diagram, is the principle clear? Okay. So, that means you have to understand that if I am going to do this, I better have a laser where cytochrome C absorbs, that means cytochrome C has an absorption band at my laser frequency, because it has to absorb the laser. See, the point is you can have a very high intensity laser, does not matter, but if your sample does not absorb the laser light, it does not matter, right, because it will just straight pass through, because it is fully transmissive, there is no absorption at all. The only way you can excite a sample or heat a sample up is you make sure that the sample actually absorbs the light you are passing through, right. That is the minimum you can do. Okay. So, thus this is what it says, at a guanine hydrochloride concentration of 4.6 molar, the photodissociation of CO will initiate the transition from the unfolded to the folded state. Okay. Since CO is known to photodissociate from the heme in less than 1 picosecond. Now, please look at this, less than 1 picoseconds, thus one in principle can observe the protein dynamics at a very fast time scale. Okay. So, what it means is you can break the bond between Fe and CO in a time scale as fast as 1 picosecond. Now, let me tell you, it is much lesser than that, it is like 100 femtoseconds or so. Okay, it is like 0.1 picoseconds or so, right. So, that means essentially the moment you have broken the bond, so let us take 1 picosecond, beyond 1 picosecond you have the full time window for you to monitor the change. So, is not this the one which gives you the fastest time of whatever techniques you have discussed? So, here therefore, this is the one which gives you the fastest time scale for you to monitor protein folding, and that is what it says. This one in principle can observe the protein dynamics at a very, very fast time scale, that means from 1 picosecond and higher. Let us not worry about how people observe that, that is a different issue, but we will not be concerned about that, but this is what the principle of the method is. You trigger folding from an unfolded situation by breaking a bond between Fe and CO, the carbon. Okay. So, essentially this is what you are doing then. If this is your folded state, this is the folded state, you have the this is the tryptophan and you have the heme in the middle. This is the unfolded state where you can see where is tryptophan, the tryptophan is here, the heme is here, right, and this is your CO. Okay. That means, if you would now break the bond, if you would now break this bond, what would happen? It would go back to the folded state, and this tryptophan would come closer to the heme in the folded state, right. So, this is in a nutshell, this is what it shows. So, you can see when you add guanine hydrochloride and CO to the folded state. So, this is the folded, it goes to the unfolded. Now, you do a H nu. What does H nu mean? That means you shine light. The moment you shine light, CO goes out, bond is broken, and it comes back to the folded state, and you monitor the rate at which it does. Okay. That means, here you are monitoring what? You are monitoring not unfolding, you are monitoring what? Folding. And I was telling you the absorption, right. So, this is the last slide. You can see the lasing wavelength was, so the laser, the pump laser, this is the pump laser, this had a wavelength of 532 nanometers. Okay. Where does 532 nanometers lie? So, this is 500. So, 532 would be somewhere here, say, okay, or maybe somewhere there. So, I am talking here, please remember I am talking about the reduced one, that means the ones with the alpha and beta, not the other one. This is the reduced side frequency I am talking about. Okay. Now, that is a different thing, but anyway, at the point of 532 nanometer, your sample does have an absorbance. So, you would absorb that light and then your bond fission would occur, and after that you can do your experiment as you are supposed to. Good. So, this brings us to the end of the techniques that at least I had planned to discuss with you. You know, to tell you the truth, more or less these are the techniques, more or less these are the most general techniques that are being used nowadays. You know, there are apart from a few other ones which are kind of a little more advanced for by people to study proteins, right. And if you would ever encounter one of these, principles are always the same, it is just how you do the experiment or how you do the final detection based on what. Like rapid mixing, both were mixing, one was a stop flow, one was a continuous flow. Then you had relaxation where you did a temperature jump. In this case you are not doing a temperature jump, you are doing a bond fission, and that is itself triggering your change in conformation of the protein. Okay.